Imagine you are a star at the edge of a spiral galaxy. You are racing around the center at 1,000,000 miles an hour. At that speed, basic physics says you should fly off into the void of space like a rock released from a slingshot. But you do not. You just keep orbiting smoothly. Why? The galaxy has a secret. There is 100 times more gravity than we can explain. Something invisible must be holding you in your lane. Something dark, something massive. We call it dark matter. The evidence for it is the reason this entire mystery exists. So here's where the evidence really begins. The 1970s, an astronomer named Vera Rubin measuring something simple, how fast stars are moving at different distances from a galaxy's center. You can do this with light itself. The same Doppler effect that makes a siren sound higher coming toward you and lower going away, light does that too. A star moving toward us shifts bluer, away shifts redder. That shift tells you its speed. Common sense says the outer stars should be slower. Think of our solar system. Mercury whips around the sun at nearly 50 kilometers every second. Pluto drifts along at under 5. Gravity gets weaker with distance, so less pull means a slower orbit. That's the rule. So you plot a graph. Distance from center on one side, orbital speed on the other. That's called a rotation curve. You expect it to slope downward like a ski jump. Easy prediction. The curve came back flat, not a gentle slope, dead flat. Stars at the very edge of the galaxy were moving just as fast as stars near the middle. Rubin checked another galaxy, same flat line, Andromeda. Every spiral galaxy she pointed her telescope at, all flat. Now picture a merry-go-round. The horses near the center barely move. The outer horses have to cover way more ground to complete one spin. They should be flying, but in these galaxies, the outer horse is going exactly the same speed as the center horse. The only way that works is if something extra is holding that outer horse in place. Add up all the visible mass in a galaxy, every star, every gas cloud, every speck of dust. It accounts for maybe 10% of the gravity needed to keep those outer stars moving that fast. The other 90% is missing. Completely invisible. We call it dark matter. So now we have a problem. The evidence says there's mass we can't see, but if it doesn't glow, doesn't block light, doesn't interact with anything we can detect, how do we know it's really there? Is it possible our understanding of gravity is just wrong? That's the question. And the next piece of evidence is about to make it even weirder. You are Vera Rubin, standing on a mountain in Arizona in 1978. It is 3 in the morning. Your fingers are numb. And the telescope is pointed at Andromeda, our closest big galactic neighbor. Your partner, Kent Ford, built a new kind of spectrograph, a fancy instrument that splits starlight into its colors so you can measure tiny shifts. He is the instrument wizard. You are the one who asks the questions. The question tonight: how fast are stars moving at the very edge of Andromeda? The old data only went out so far. No one had pushed to the outer rim before. You expected confirmation. A simple graph showing the outer stars slowing down, exactly like planets in our solar system. You collect the first data point from a star halfway out. Speed looks normal. You keep going, farther out. Another point, still fast. You go all the way to the edge, where gravity should be barely a whisper. The star is screaming along at nearly the same speed as the inner ones. This is not a small error. This is the entire prediction being wrong. Ford double-checks the instrument. No mistake, Rubin plots the graph. The curve is flat, absolutely flat, which means the mass pulling on these outer stars cannot be just the stars we see. That mass would only produce 1/10 of the gravity needed. The rest must be something else, something invisible. So she does what any good scientist does. She checks another galaxy, same flat line, then another, and another, spiral after spiral, all of them showing the same pattern. It is not a fluke. It is a universal rule. Here is what that means. The stuff we can see, every star, every nebula, every planet, makes up maybe 5% of the total mass of the universe. The rest is dark. We cannot see it, we cannot touch it, but we can measure its gravity. Rubin did not set out to discover dark matter. She just wanted to understand how galaxies spin. Instead, she proved that everything we thought galaxies were made of is just the froth on top. The real mass is hiding in the dark, and it gets worse. Because if the missing mass is real, it has to be everywhere, including right here in our own galaxy, passing through you right now, but more on that later. You are an astronomer in 1987. You take a picture of a cluster of galaxies. You expect to see one galaxy behind it. Instead, you see 5 copies of the same galaxy forming a perfect ring. That is not a camera glitch. That is not a weird reflection. That is a cosmic magnifying glass. Here is the rule you learned in school: light travels in straight lines, always, except, and this is the part your teacher glossed over, gravity bends space itself. So when light passes near a massive object, the space it is traveling through gets curved, and the light has to follow that curve. The light thinks it is going straight. To us, it looks bent. Now replace the massive object with an entire cluster of galaxies. That cluster has so much gravity it acts like the lens in a pair of glasses. The light from a galaxy behind the cluster gets magnified, warped, sometimes duplicated into multiple images. This is strong lensing. It produces beautiful arcs and rings, but that only happens when the alignment is perfect. Most of the time, the effect is subtle, just a tiny stretch. Imagine looking at a crowd through a wavy window. Each person is distorted by a barely noticeable amount. That is weak lensing. You take millions of background galaxies and measure their average shape. If they all point in the same direction, something massive must be distorting them. So you map where the stretch is happening, and that tells you exactly where the mass is. The visible galaxies are in one place. The mass map says the gravity is somewhere else, in the empty space between them. That empty space is full of dark matter. The light is not bending around nothing. It is bending around something we cannot see, and that something forms a web that holds entire clusters together. We are not just detecting dark matter anymore. We are taking its picture. But we can go further back, to the first light. You are a photon, 8 billion years, and you are cold, barely above absolute zero. You might be thinking, how does a frozen photon help find dark matter? That seems absurd. That photon is part of the cosmic microwave background, a baby picture of the universe at age 380,000 years. Here is how that picture was taken. In the beginning, the universe was a hot, dense soup. Too hot for atoms. Electrons and protons bounced around like bumper cars. Light could not travel far, it kept scattering off particles. It was a fog, but in that fog, sound waves rippled. Pressure waves like sound in air, but they pushed and pulled on the matter. They compressed some regions and stretched others. Think of those sound waves like a spring. Gravity pulled in, pressure pushed out. They oscillated. Then, when the universe cooled enough for atoms to form, the bumper cars stopped. The fog cleared. The sound waves got frozen in place. And the light that had been scattering suddenly traveled freely. That light carried the imprint of the sound waves. Hot spots where matter was compressed, cold spots where it was stretched. That light is the CMB. Now, when we look at that baby picture, we see a pattern of spots. The size of those spots is a fingerprint of the universe's ingredients. Here is the part that breaks your brain. You might assume those sound waves only involved ordinary matter, protons, electrons, the stuff we are made of. And they did, but when we measure the pattern, it does not match a universe with only ordinary matter. The spots are too big, which means the sound waves had extra gravity pulling on them. Gravity from something that was not part of the fog, something that did not participate in the bouncing. It just sat there, adding its weight. Dark matter. The sound waves could not bump into dark matter, but they felt its gravity. So the pattern only makes sense if dark matter made up about 27% of the total energy density of the early universe. That is not an assumption. That is a measurement from the oldest light we can see. So the CMB is not just a baby picture. It is a confession. Dark matter was there from the beginning, hiding in the background, bending the sound waves. 3 independent lines of evidence now point to the same thing: the galaxies spinning too fast, the warped light of lensing, and now the pattern from the beginning of time. Dark matter is not just a guess. It is the only explanation that fits all 3. You are a galaxy in the Coma cluster. You are moving at 1,000 kilometers per second. That is fast enough to cross the entire United States in 3 seconds, and you are not alone. Thousands of galaxies fly around you at similar speeds. Here is the problem. At that speed, you should have escaped the cluster long ago, but you haven't. Something is holding you back. That doesn't add up. If the cluster only contained the mass we can see, stars, gas, dust, its gravity would be too weak to keep you bound. You would fly off into intergalactic space. So why are you still here? The obvious answer. Maybe there is more mass hiding in the dark. But Fritz Zwicky, a Swiss astronomer in 1933, took that idea and made it sound insane. He measured the velocities of galaxies in the Coma cluster using the Doppler shift, the same way a siren changes pitch when an ambulance passes. He found they were moving so fast the cluster should have flown apart. He calculated the mass required to hold it together and got a number 400 times larger than the visible mass. 400 times. That is like weighing a child and then being told you actually need 400 children to hold down a tent in a hurricane. The math said there was something there, but nobody could see it. Zwicky called it Dunkelmaterei, dark matter. Skip forward a few decades. X-ray telescopes discovered that galaxy clusters are filled with hot gas, millions of degrees hot. That gas is so energetic it should boil away into space, unless the cluster's gravity is enormous. When we calculated the mass needed to keep that gas trapped, we got exactly the same numbers Zwicky did. We have now repeated this measurement on hundreds of clusters. Every single one tells the same story. The visible stuff accounts for maybe 1% of the total mass. The rest is dark. So Zwicky was not wrong. He was just early. He found the weight of galaxy clusters, and that weight told him something was missing. It took us nearly a century to catch up. You are the law of gravity. Isaac Newton wrote you down in 1687. Double the distance and the pull gets 4 times weaker. It works for falling apples. It works for orbiting planets. But then a galaxy spins, and the stars at the edge move as if the center is tugging 10 times harder than you allow. So maybe you're the problem. Weird thought, right? That the most tested rule in history might need a patch. But some physicists took it seriously. They asked, what if gravity doesn't drop off as fast at very large scales? That is MOND, modified Newtonian dynamics. It says when gravity gets extremely weak, it stops obeying the square rule and decays more slowly. So at the edge of a galaxy, the pull is stronger than Newton predicted. This one change makes the rotation curve flat. No dark matter needed. Okay, problem solved. Except for the parts that break entirely. First, galaxy clusters. Even if you apply MOND to the Coma cluster, there is still way too much missing mass. You still need something invisible. Second, the Bullet cluster. 2 clusters collided. The hot gas got tangled and slowed down. But the gravity, measured by how light bends, is not where the gas is. It is offset, exactly where dark matter should be material that passed right through. MOND cannot explain that separation without adding dark matter anyway. Third, the cosmic microwave background. The pattern of spots from the early universe needs a collisionless component that does not interact with light, but pulls on matter gravitationally. Without it, the spots do not line up. So MOND explains one piece of evidence and fails on everything else. Dark matter might be invisible, but it is simple. One ingredient fits galaxy rotations, clusters, collisions, and the universe's baby picture. Changing gravity is like patching a single hole while ignoring the rest. Dark matter is not a guess. It is the least creative explanation that actually works. 4 independent lines of evidence converge on one conclusion. Something invisible makes up 27% of the universe. That means everything we see, stars, planets, me, is just a fraction. So here is the question that keeps astronomers up at night. What else might we be completely blind to? Drop your best dark matter theory in the comments. And if this video changed how you see the sky, share it. I will see you in the next one.